so let's start the session. So in last lab we performed the experiment number 5. So today we have to perform the experiment number 6. So in last lab uh, we performed the experiment which is known as the binary to gray conversion and gray to binary conversion. Okay, so binary to gray and gray to binary. So now in this lab we have to perform the experiment number 6, which is the code converter. Which is a comparator. So in last lab we performed the experiment which is known as a code converter. So in that code converter we learn about the circuit which is used to convert binary code into a gray code and gray code into a binary code. So today we have to perform the experiment which is a comparator. So in comparator, suppose we have two numbers. We have two numbers and we have to compare these two numbers. We have to compare those two numbers. So how we can compare those two numbers and which is the circuit used for the comparator, that we have to perform today. So generally the comparator, suppose I have a two number A and B. I have two numbers, you can say A and B, and I have to compare those two numbers. I have to compare those two numbers. So there are three generally possibilities while we comparing the two numbers. Either you can say A equal to B, or you can say A greater than B, or A less than B. So these three are the possibilities of the comparator. These three are the possibilities of the comparators. So also there are the different types of comparator which we have. It is a 1-bit comparator, you can say 2-bit comparator, 4-bit comparator. Okay, so 1-bit, 2-bit and 4-bit comparators which we have to learn. So let me share my screen. So again, we are using the virtual lab tool, and we are using a virtual lab which is designed by the IIT Bombay. So let's move for the list of experiment. So actually this is our experiment number 6, and in virtual lab it is experiment number 12. So it is the last experiment in the list of experiment in virtual lab. So this is the aim to verify the truth table of a 1-bit comparator and a 2-bit comparator. Okay, so this is the actually aim. We have to verify the truth table of 1 bit and a 2 bit comparator by using a logic gate. So how actually 1 bit and 2 bit comparator will work? Also, there are the 4 bit comparator also, but we have to study about the 1 bit and a 2 bit comparator only. So let me give you the brief about what is the comparators. So actually comparator is a logic circuit, or you can say it is a combinational circuit. Okay, it is a one type of combinational circuit which is used to compare the magnitude of two binary numbers, which is used to compare the magnitude of the two binary numbers, magnitude of a two binary numbers. So we have a three different possibilities for that. We have three different possibilities for that. Suppose we have two binary numbers known as A and B. So we have you can say three different possibilities when we are comparing the magnitude, where we are comparing the magnitude of A and B. Either it is A equal to B, or you can say it is A greater than B, or it will be A less than B. So A equal to B, A greater than B, and A less than B. Okay. So comparator is a one type of a combinational circuit which is used to compare the magnitude of two given binary numbers. And that combinational circuit are made by the logic gates, you can say. So most of the circuits are made by the so now generally the XNOR gate are the, you can say, a basic comparator circuit. Why XNOR gate are known as a basic comparator circuit? Because if you are know about the truth table of the XNOR gate, so let me tell you about the truth table of XNOR gate. XNOR gate having a truth table like this: 0 0 it is 0, 0 0 it is 0, for 0 1. Sorry, the XNOR gate, the truth table is for 0 0 it is 1, 0 0 it is 1, for 0 1 it is 0, for 0 1 it is 0, for 1 0 also it is 0, for 1 0 also it is 0, and for 1 1 it is 1. For 1 1 it is 1. So when the output of an exclusive NOR gate is high, when both the inputs are same, then and then the output of the exclusive NOR gate is 1. Let's say for 0 0 also it is 1, and for 1 1 also it is 1. But when the inputs are different, the output of the exclusive NOR gate is 0. When the inputs are different, let's say either it is 0 1 or 1 0, its output will be 0. So when the output is 1, when and only when all the input bits are coincide with each other. Coincide means same. What is the meaning of coincide? It is same. So when all the inputs are same, either all are the zeros or all are the ones, then and then the output will be 1. Then and then the output will be 1. So the exclusive NOR gate is known as the basic comparator circuit. Okay. So the two more binary numbers are equal if and only if the two binary numbers are equal, if and only if all their corresponding bits are coincide. What that means? All their corresponding bits are same. Okay. So suppose we have two binary numbers A and B. we have a two binary numbers A and B, and both the binary numbers having a 4 bits. Both the binary number having a 4 bits. Suppose the in A binary number we have 4 bits. Let's say A3, A2, A1, A0. And in another binary number B, again we have four binary bits. Let's say it is B3, B2, B1, and B0. So when A is equal to B, we can say A equal to B when all their corresponding bits when all their corresponding bits are coincide with each other, or you can say it is same. So if my A3 equal to B3, A2 equal to B2, A1 equal to B1, and A0 is equal to B0, then we can say A equal to B. Then we can say A equal to B. So all the four bits must be coincide with each other for the equality possibility. And the equation for that is H3, this symbol in between. This is the symbol of exclusive. This is the symbol of exclusive NOR gate. So A3 if coincide with B3, A2 coincide with B2, A1 coincide with B1, and A0 is coincide with B0, then we can say A equal to B. So today we have to learn about do the experiment about the 1-bit comparator and a 2-bit comparator. Okay, 1-bit and a 2-bit comparator. So let's say again we have two numbers A and B, and those two numbers having only a 1 bit. So let's say the bit in A, it is A0, and B0 is the bit of a number B. So when we can say that A greater than B, if my A0 is 1, and B0 is 0. If my A0 is 1 and B0 is 0, then we can say A is greater than B. What is the possibility of A less than B? Suppose my A0 is 0, and my B0 is 1. A0 is 0 and my B0 is 1, then we can say A is less than B. And what is the possibility of A equal to B? Let's say my A0 is 0 and also my B0 is 0, then A equal to B, or my A0 is 1 and my B0 is also 1, then also we can say A equal to B. So what is the expression for A greater than B? You can see I already said lots of time. Generally we have to learn about we focus on the SOP only, it is sum of product, and when 0 means bar and 1 means as it is. Or you can say 0 means dash and 1 means as it is. So the equation of A greater than B is A0 1, B0 is 0. So 1 means as it is, so A0 and B0 is 0 means B0 bar. So the equation of A greater than B is A0, B0 bar, or you can say A0, B0 dash. Now the possibility of A less than B, for A less than B, my A0 is 0 and my B0 is 1, then we can say it is A less than B. And again the equation of A less than B is A0 bar B0. A0 dash B0, because the value of A0 is 0. So A0 dash B0. Now last for the equality. If my A0 is equal to 1 and also my B0 is equal to 1, then we can say equal to B. Also, if my A0 is equal to 0 and B0 also is equal to 0, then also we can say A equal to B. And the equation for the A equal to B is A0 exclusive NOR B0. A0 exclusive NOR B0. So this is the equation for that. A0, this is the symbol of exclusive NOR B0. So let's make a truth table. So from the truth table, you can easily see my A0 and B0 for 0, 0. So both are 0, 0. So both are 0, 0. So you can easily see both are 0, 0 means it is equal. So less than, and L means less than, E means equal, and G means greater than. Okay, less than, equal, and greater than. So 0, 0 means both are same. So E is 1. For 0, 1, so A is less than B. So my L is 1. All other are 0. For 1, 0, A is 1 and B is 0. So it is a greater than. So my G is 1 and all other are 0. And both are 1, 1. Means it is equal. So my L and G is 0, 0 and E is 1. So this is the truth table of the 1-bit comparator. Now we have to draw the circuit. So A0, B0 coincide. So we have to use the exclusive NOR gate. So here I am using the exclusive NOR gate. So this is the A equal to B. For A greater than B, my equation is A0, B0 dash. So I am taking B0 from here, connecting with a NOT gate. And I am taking A0 directly, connecting with a AND gate. Then it is the circuit of A greater than B and A less than B. So this is the logic diagram. What is the circuit of A less than B? A0 dash B0. So I am taking A0, connecting with a NOT gate. So here I get the A0 dash. Here I am getting B0. So A0 dash B0 is for the A less than B. And A0 B0 dash is the circuit of the A greater than B. So this is the theory, or you can say a truth table and the logic diagram. Truth table and the logic diagram for the one-bit comparator. Logic diagram of a one-bit comparator. Anyone having any doubt in a one-bit comparator? If anyone having any doubt in a one-bit comparator, you can unmute yourself and ask me a question, or you can ask me a question in a chat session. And if it is clear, please write down clear in a chat session. Then we will move forward. I am waiting for your reply. Only 1 out of 90 give me the reply. What about others? Either it is clear for you or it is not. Okay, thank you. So let's also check the theory for given in the virtual lab for the 1-bit comparator, and then we will move for the 2-bit comparator. So you can see so magnitude is the digital comparator, is the combinational circuit that compares two digits or a binary numbers in order to find out either it is equal to or a less than or a greater than. So we have in a comparator, or you can say any bit comparator. N bit comparator, we have always two input, which is A and B, and as we have a two input A and B, we have a three different possibilities for the output. Either A is greater than B, or A is less than B, or it is A equal to B. So this is the generalized block diagram of a comparator which having a two input and three output, two input and three outputs. So again, one bit comparator. So one bit comparator is used to compare the two bits. So it consists of two input again, and which having a three output, or the three output is less than, equal to, and greater than. So this is the truth table which we already see. For 0, 0, it is A equal to B. For 0, 1, it is A less than B. For 1, 0, it is A greater than B. And for 1, 1, again it is A equal to B. And this is the equations which we already derived. And this is the some different circuit which is used for the again comparator. Now let's move for the 2-bit comparator. Again, 2-bit magnitude comparator. So again, we have two binary numbers A and B, but now these two binary numbers having a 2 bits. You can say A is equal to A0, A1, and B is equal to B0, B1. Now we have to compare these numbers. So what is the combination for A greater than B? So now you can say A1 is the most significant bit, or you can say it is having a highest weightage compared to A0, and it is in B. B1 is the highest weightage. B1 is the highest weightage compared to B0. So if my A1 is 1 and my B1 is 0, then we do not have to check A0 and B0. Then we do not have to check A0 and B0. Let me tell you why it is. Let's say my A1 is 1 and my B1 is 0. And then suppose my A0 is 0 and my B0 is 1, then also if you convert into a decimal, it is 1, 0 means 2 and 0, 1 means 1. So my A is greater than B. So if my A1 is 1 and B1 is 0, then we do not have to focus, on other bits, A0 and B0. But suppose my A1 and B1 is same. My A1 and B1 is same. You can say, suppose either my A1 is 0 and my B1 is also 0, or my A1 is 1 and my B1 is 1. So second case, if my A1 and B1 is same, then we have to focus on A0 and B0. Then my A0 must be 1 and my B0 is 0. Then and then we can say it is A greater than B. So second possibility is, if my A1 and B1 is coincide. What is the meaning of coincide? The meaning of coincide means it is same. So if my A1 is same with a B1, so A1 is coincide with B1, then we have to focus on A0 and B0. Then we have to focus on the A0 and B0. At that time, my A0 must be 1, my A0 is must be 1, and my B0 is 0. Okay. So the equation of A greater than B is, we have the first condition. You can say A1 1, B1 0 means A1 B0 bar, sorry, A1 B1 bar. And suppose my another possibility, or means add A1 and B1 coincide and A0 1 and B0 0. So the equation for A greater than B, you can see this is for the first case, A1 B1 bar, and this is for the second case. If my A1 and B1 is coincide means if it is same, then we have to focus my A0 must be 1 and B0 must be 0. Okay. So now let's move for the another possibilities. So now for A less than B. So for A less than B, my A1 must be, if my A1 must be 0, then my B1 must be 1. If my A1 is 0 and B1 1, so we do not have to focus on A0 and B0 at that time, because my MSB of A1 is 0 and MSB of B1 is 1. So we do not have to focus on the A0 and B0. My A must be less than B. My A must be less than B. But suppose my A1 and B1 is same. So you can say my A1 is coincide with B1. My A1 is coincide with B1. Okay. Then we have to focus on the A0 and B0. Then we have to focus on the A0 and B0. So at that time my A0 must be 0. At that time my A0 must be 0 and my B0 is 1. My B0 is 1. Then and then we can say my A is less than B. My A is less than B. Okay. So this is for the A less than B. Now again, let's focus on the equation. So this is the equation for A less than B. So this is the A1 bar, A1 dash B1 is it is for the first case, A1 dash B1 it is for the first case. And if my A1 is coincide with B1, then A0 dash B0. Then A0 dash B0 is for the second case, case number 2. Now we have a third possibility. You can see for A equal to B. So again, when the A equal to B, if my A1 and B1 is coincide, as well as my A0 and B0 is coincide, if my A1 and B1 is coincide, as well as my A0 and B0 is coincide, then and then I can say, my A equal to B. Then and then I can say my A equal to B. Okay. So the equation for A equal to B is A1 is coincide with B1, and also my A0 is coincide with B0. A0 is coincide with B0. Then and then we can say A equal to B. Now again we have to draw the logic diagram. So so these are the equation of A greater than B, A less than B, and A equal to B. Okay, so you can see it is in your screen. So for A equal to B, we have A1 is coincide with B1 and A0 is coincide with B0. A1 is coincide with B1 and A0 is coincide with B0. So we require two exclusive NOR gate. We require two exclusive NOR gate, one for the A1 and B1 and another for the A0 and B0. So see, this is the A1 B1. We are using one exclusive NOR gate. So here A1 is coincide with B1, giving to the one AND gate, and A0 is B0 with coincide. A0 is coincide with B0. Again, we are giving to the another input as AND gate. So finally, we have the equation. Finally, we have the equation for the A equal to B. Finally, we have the equation for the A equal to B. Then we have to equation A greater than B. So you can see here A greater than B, we have A1 B1 dash. A1 B1 dash. So A1 I am taking directly, B1 dash. So A1 B1 dash plus. So for plus we have OR gate. A1 coincide with B1. So here we have A1 coincide with B1. So I am taking A1 coincide with B1. Also multiplying with A0 B0 dash. So I am taking A0 and B0 dash. Again giving to the OR gate. So finally we have the circuit of A greater than B. Finally we have the circuit for A greater than B. And now the circuit for A less than B. So for A less than B, we have A1 dash B1, A1 dash B1. So you can see here A1 dash B1 giving to the one AND gate. Okay. And then we have A1 exclusive NOR B1. So again, I am taking A1 exclusive NOR B1 here. And we have A0 B0 dash. So A0 dash B0. So A0 dash B0. So giving to the OR gate. So this is the equation of AX less than B. So this is the logic diagram. This is the logic diagram of the 2-bit comparator. If the 2-bit comparator will be asked, it will be asked many times in GTU, either in 4 marks or 7 marks. Many times it will be asked. If you refer the past GTU papers, you can uh, see that 2-bit comparator will be asked in 4 marks or 7 marks. So you can see here. We have to derive the equation for the A equal to B, A less than B, and A greater than B for the 2-bit comparator, and then we have to draw a logic diagram. So this is the equation and the logic diagram of a 2-bit comparator. Now anyone having any doubt in a 2-bit comparator? If anyone having any doubt in a 2-bit comparator, you can unmute yourself and ask me a question, or you can ask me a question in chat session. So I think there is no doubt from anyone. So again, let's check the theory portion, which is given in the virtual lab. Again, this is a 2-bit magnitude comparator. So again, we have a 2 inputs and the 3 outputs. The 3 output is less than, equal to, and greater than. So now check the truth table, which is not given in the theory session. So you can see here, if my A1 A0 and B1 B0 are same, so 0 0 0 0. So what that means, my A equal to B. Suppose my A1 A0 is 0 0, my B1 B0 is 0 1. So again it is a 4-bit number. So we have a different 16 possibilities starting from 0 0 0 0 to 1 1 1 1. Okay, so 0001. So again for 0001 my A less than B. 0010. So for 00 and 10 again my A is less than B. 0110. So 0110 again my A is less than B. 0011 again my A is less than B. Now 0100. So for 0110, for 0100 A greater than B, and for 0101 my A equal to B. Same way you have to check each and every time A1 A0 and B1 B0, and then you have to make the truth table for the A equal to B or A less than B or A greater than B. So this is the truth table, and from the truth table you can easily derive the equation. When my output is 1, you have to write its input condition. So this is the logic diagram of the 2-bit comparator. So these are the some of the application of comparators. Let me zoom it out so you can aware about that. What is the actually application of the comparators? So the first one is comparator are used in a central processing unit. You can say CPU, and in a microcontrollers. Okay. If you want to compare the two numbers, we have a program. So comparators are in microcontrollers also, and it is in CPU also. Also, there are some physical application of the comparator. Suppose you can take uh, the example of AC, air conditioner. Suppose your room temperature is 30 degree. Okay, your room temperature is 30 degree, and you start your AC and set a temperature of 23 degree in your AC. So what your AC will check? So your AC will check the room temperature and temperature which is set by you. So again, in AC also there are a comparator. So it compares the two temperature, the room temperature and the temperature set by you. So if the room temperature and the temperature set by you having a different temperatures, so your room temperature is higher than the temperature set by you, so your AC will start and it makes your room temperature or adjust your room temperature and make your room temperature at the temperature which is set by you. And when both the temperature are same, suppose you are setting your AC temperature at 23 degree and now your room temperature is also 23 degree. So now comparator gives the signal to the AC, and the power is cut off. So supply is cut off and now your AC is switch off. Again, if your room temperature is higher than your again your room temperature is higher than your AC temperature. So again the comparator compares the two temperature, and again your AC will be start automatically. So it is a one type of programming, you can say, but for that programming we require the comparator. So comparator is also compare the physical variables like a temperature and position for the control application. For controlling we use the comparators. Okay. So this is the second application. Again, the third application is the comparators are also used as a process controllers and the servo motor controllers. So again, the servo motor is a type of you can say position control. So it is also used in servo motor application. And the last one is the comparator is also used for the security purpose also. Suppose you have a bimetallic strip and you set your strip. So each and every type, if your bimetallic and is sense, and if it is same, then and then your door will be open. So again, we have to use comparator there. So comparator is also used in password verification and the biometric application. So these are the some of the application of the comparators. Okay, so these are some of the application of the comparator. So now anyone having any doubt in this theory session? If you have a doubt, you can ask me a question. Otherwise, we will move forward for the, you can say, uh, experiment. Oh, sorry. Before that, we have to move for the pre-test. And if it is clear, please write down a clear. So I will move forward. Okay, so thank you everyone. So now let's move for the pre-test. Now it's your turn. You have to give me the answer. Okay, so all the comparison made by a comparator. The first question is all the comparison made by a comparator is done using one circuit, two circuit, three circuit, or four circuit. So either answer is A, B, C, or D. Okay, so Jenny, Mahima, Bhavesh gives the answer. What about others? Rajesh, Parth, Isa, Rutvi. Okay, so almost all are giving the same answer. J, it is A. Now, one that is not the outcome of a magnitude comparator is either it is A greater than B, or it is A minus B, or it is A less than B, or it is A equal to B. So which one is not the outcome of the magnitude comparator? A, B, C, or D? Okay, so Parth, Jenny, Mahima, Bhavesh, Anand, Chintan, Lisa, Kunal gives the answer. It is B. J. Okay. So the third one. If the two numbers are not equal, if the two numbers are not equal, then binary variable will be it is 0 or 1, or it is A or B. So A, B, C, D. Okay, Mahima, Jenny, Anand, Chintan, Ravi, Krunal, Oho, Parth, Bhavesh, Jay, Lisa gives the answer that it is 0. Okay, very good. The next one. The which one is a basic comparator? Which one is a basic comparator. So which we are using for the basic comparator? Rajesh, Mahima, Chintan, Anand. Okay, so almost all of you are giving the right answer. It is the exclusive nor. The last one. The comparators are used in. Okay, I do not have to read options also. Almost all you are giving the answer. It is the CPU. Okay, so let me submit the quiz. We will check how many our. Okay, so all the answers are right. All the answers given by you, it's right. Okay, so let's move for the what we can say procedure. Again, the procedure is common for most of all. We have the switches. So we have two inputs here. Instead of input A and B, we have the input X and Y. So it's same. Either it is A and B or it is X and Y. It doesn't affect. So we have to compare the this by switch on and off, and also we have a switch for the power supply because the for IC we require the power supply. So let's move for the simulation. So I'm sharing the link with all of you. So now you have to do the simulation by yourself. Okay, so start the simulation by yourself, and if you have any issues or any problem or any doubt in a simulation, you can ask me a question. Okay, so start the simulation. So there are two simulators, 1-bit comparator and a 2-bit comparator. Now, can anyone share their screen? So anyone having any issue regarding the experiment? Can anyone find the difficulty by performing the experiment? So no one find any difficulty. Uh, Let me show you. So let me click on the 1-bit comparator. Okay. Let me reduce the. So first we have to give the supply to the each and every IC. Without supply, the IC will be not work. And this IC requires the 5-volt supply. So switch on the supply. So now my both the input is 0 0. So you can see my equal to both the input is same. So the equal to LED is glow. Add to the table. Now 0 1. So my x is 0, my y is 1. So my x is less than y. Add to the table. Now 1 1. Again x equal to y. So add to the table. And 1 0 you can say. So x is greater than y. So it is really easy for the simulator 1. Now click on the simulator 2. We have a different simulator. So let my a is 0, b is also 0. So my a less than b is 0, my a equal to b is 1, my a greater than b is 0. Take to the table. If it is correct, it will write like it is correct. Then my a is 0, b is 1. What that means? My a is less than b. So my a less than b is 1. All are 0. So click on check. Now again it is correct. Let my a is 1, my b is 0. So again my a is greater than b. So click on that. So write down. So again it is same. And for 1 1, again my a equal to b. Click on the check. You can see all are the corrects. So I think all of you are already done. Now let me show you about the 2-bit comparator. Can anyone perform the 2-bit comparator or complete the 2-bit comparator? Okay. So again, see, all are zero zeros. 0, 0. So x1, x0 also 0, y1, y0 also 0. So it is A equal to B. You can see here A is equal to B. Add to the table. These are the some color codes in which how the IC will be connected to the each others, because we required more numbers of ICs and more numbers of gates. So that's why it is. Then my suppose 0001. So for 0001, my AX is less than Y. So again add to the table. So then 0010, again X is less than Y. Add to the table. Why I show you? Because you have to take the printout of this. You have to make a menu. Okay, you have to make a lab menu of this. From this, you can just click on the printout, and from that, if you click on the printout, you can easily save this image. You can easily save this image. Okay. So after 0010, it is 0011. Again 0011, my X is less than Y. Now there is a time of greater than. So 0100 for 001, my X is greater than Y. Then 0101, if 0101 means X equal to Y, add to the table. Then 0110, 0110 means X is less than Y. Then 0111, again X is less than Y. Next one is 1000. So 1000 is A greater than B. 1001, again A greater than B. Next is 1010. So 1010, it is equal. 1011, again less than. Next is 1100, again it is greater. 1101, again it is greater. Now all the ones, again it is equal. And one is missing is 1110. Again it is greater than. So this is the table. Okay. What you have to do, sir, just click on a print. So this is the table you can get. Also, you can change the layout from uh, portrait to landscape. So you can easily take a printout or take a screenshot. Okay. So now can anyone complete its simulator 2? Because I have very much doubt in simulator 2. It will not work. So no one have any query on simulator 2. So I think all of you are complete that. But I having a doubt in simulator 2 of a 2-bit comparator, it will not work. So suppose if you are writing here A0, B0. So it's same. So suppose A less than B, you are writing 0, A equal to B, you are writing 1, and A less than B, you are writing 0. Click on check, it shows you are incorrect. Okay, let's take all the zeros, then also it's incorrect. Suppose if you are thinking it is A greater than B, you can click on check, again it is incorrect. Suppose if you are checking it is A less than B, again click on a check, it is incorrect. So last thing, suppose if you are taking all the ones, it's not the case, but suppose, then it is again incorrect. So, I think no one can check the simulator 2 for the 2-bit comparator. Otherwise, out of 20, anyone can raise the query. Okay. So, the simulator 2 of a 2-bit comparator is not working. So, there are a problem with a simulator 2. So, it is not working properly. Okay, so we do not have to focus on the simulator 2 for the 2-bit comparator. Okay, so now let's move for the post test. Now again, I am asking if anyone having any doubt. Anyone having any doubt? Or if it is clear, please write down clear. So we will move forward and we'll go to the post test. Okay, so let's move for the post test. Let me zoom it out. Okay, now give me the answer. The first question is the purpose of a digital comparator is to convert analog into decimal, create different outputs, to add a set of different numbers, to compare a set of variable or unknown numbers. So either it is A, B, C or D. What is the answer? What is the actual purpose of comparator? Okay, Mahima, Jenny gives the answer. What about others? What is the application of comparator? Okay, Parth, Lisa, Isa. Okay, so most of you, not most of all of you are giving the same answer. It is D. Okay, so our next question. A magnitude comparator is defined as a digital comparator which having how many outputs? One output, two output, three output, or no output terminal. So comparator, the comparator which how many outputs comparator have? Only one output terminal comparator have, two output terminal, three output terminal, or no output terminal. Okay, so Mahima, Jenny, Lisa gives the answer. It is the answer given by them. It is C. So the three output terminals. So the comparator having a three output terminals, and it is really correct. The comparator having a three outputs, either A greater than B, or it is A equal to B, or it is A less than B. So comparator having a three outputs. In a comparator, if we get input as A greater than B, then the output will be B, 1, A, 0. So A, B, C or D. Okay, Jenny gives the answer. Mahima gives the answer. Isa gives the answer. Okay, Parth also gives the answer. So the same answer all of you are giving, it is B. So 1. The next one. How many inputs are required for the digital comparator? How many inputs? we have required for the digital comparator. It is 1, 3, 2 or 4. So A, B, C or D. Okay, Mahima gives the answer, Jenny, Isa, Lisa gives the answer, the same answer given by all of you, it is C. Okay, Rajesh also gives the answer. So we have two inputs generally in a digital comparator. Okay. The last one. The identified comparator is defined as a digital comparator which has only one output terminal, two output terminals, three output terminals, or no output terminals. So either it is A, B, C or D. Okay, so Mahima and Jenny gives the answer, it is A. Okay, Rajesh also gives the answer. Let's click on that and let's submit the quiz. Okay, Lisa also gives the answer, it is A. Okay, so very good, all of you. All of you are giving the right answers because we are getting 5 out of 5 correct. So all the 5 answer is correct. So if no one understand what is the actually identified comparator, it's it gives output only when all the inputs are same. So it is a single output only. Okay, so it compares the two bits, but it do not have three output terminals like A equal to B, A less than B, and A greater than B. It having only one output for the A equal to B. So all the answers are correct. So and at last we have also references. So if you want to learn more about the comparators and how the comparators will work, you can check the references in which we have a numbers of reference books, and also we have a links and YouTube video. So in YouTube video, you can learn how to make a comparator in a breadboard. You can click on that. It's again the theory about the comparator. And at last, these are the three ICs we are using for the comparator: AND gate, exclusive NOR gate, and a NOT gate. And how it will be work, and it will be connect the three LEDs at last. So you can see it is for the A and B 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So you can check the video also if you want to learn more about the comparator. So now anyone having any doubt or a query, you can ask me right now. Otherwise, we can end the session. Okay, so thank you everyone for attending the session. So please write down your enrollment number for the attendance. And after that, we will end this session. And those who already written their number, if they want to leave, they can leave the session. So thank you everyone. Now I am ending the session. લોસ એટલા છે ને એટલે હવે ડિલિવરી ચાલુ કરી છે. જાજુ કરવાનું નહીં, ખાલી જોવાનું માર્કેટ બહુ જાજુ. ગયા મહિને આખો પગાર વયો ગયો મને. યા ઓલા કોલ પુટ જ હોય ને. એ તો પ્રોબ્લેમ થયો ને ભાઈ.